So I'm pleased to inform you that Dr. Zubrin is a candidate for the Board of Directors of the National Space Society and is the pride of the space activist slate as an outstanding example of someone who is actually working to create communities beyond the Earth.
Drop me a note. It's the easiest way to do it.
The dry statistics are that he has a Master of Science in Aeronautics and Astronautics, that he has a PhD in nuclear engineering at the University of Washington, that he's a senior engineer at Mark Marietta Astronautics in Denver.
I have to prove to someone you're here.
But the exciting thing is that he's up to tomorrow, for example, he'll give us an update on Mars exploration and colonization. And today, he will talk about an advanced space transportation concept that he and his team have been involved with, including a magnetic sail. In fact, I'm so impressed with this gentleman, I'm going to ask him if he would please take a copy of my resume back to Denver with me. So, ladies and gentlemen, please welcome Dr. Robert Zubrin.
Okay, my talk today is on advanced space transportation concepts. Those of you who know me or know of me know that I've done a lot of work on Mars exploration. And I'm going to be talking about that tomorrow. I'm not really going to talk about near-term Mars exploration or colonization today. I will talk about that in my talk tomorrow. Instead, what I'm going to talk about here is various innovative concepts that I've been involved in one way or another that I think have potential to move things forward in order of magnitude or so. One of them is the magnetic sail, and when I put this talk together, I was debating whether I would talk about a large number of concepts and just a little bit about each one, or whether I would do basically a rather long and in-depth treatment of the magnetic sail. And I compromised, and I decided I'd do one short treatment and a good treatment of the sail, basically. So I'm just going to talk two main concepts today. May I have the first slide? I'll start with the short one. This is a concept that I call a hypersonic skyhook. Now, everybody, or a lot of you, have heard about the idea of the skyhook. I believe the first serious paper on that was Jerome Pearson's in the mid-70s. There was also a Russian paper at about that time. And what that concept was that Pearson would put a satellite in geosynchronous orbit, okay, so that it had no motion with respect to the ground, and extend a long cable down from it, and basically establish a cable car to orbit. And you would need no propellant, you would just need the energy required to lift something up that cable, and it turns out that it would be a system that could lift things to orbit for a few cents a pound. Would be great, except there was a major problem with it, which is that if you put a certain load at the end of the tether, then at the bottom of it, then the tether that's holding it up has got to have enough strength to hold up that load, and the piece of tether above that has to have enough strength to hold up the load plus the piece of tether below it, and so it gets bigger. And then the next piece has to hold up everything below it, and it starts expanding exponentially. And what you would have to do is you have to taper the tether so the bottom would be small, though it can't be that small, it has to hold the given load. And then it would exponentially get fatter, and the ratio between the area at the bottom of the cable and the top at the satellite would be what they call the taper ratio. And it would turn out that with current materials, it would be enormous. You'd be talking about taper ratios of 10 to the 10th, 10 to the 20th, pick a number, okay? I mean, they were just incredible kinds of objects that would be discussed, and you'd be talking about, to lift a 10-ton object, you'd be talking about something that would weigh billions of tons, and clearly, you know, putting a billion-ton object in orbit is a formidable task. And so forth, so that while the idea was conceptually beautiful, unless you postulated extremely advanced materials with hundreds of times existing strength to weights. Because if you can do that, then everything starts getting nice. But with current or near-term materials, it was sort of very speculative. Now, subsequently, people started looking at how they could improve this, and there were a number of ideas advanced. Hans Moravec in particular is one who advanced the idea of, well, gee, what if you spin the tether, rotate it, and then you see what you could have. You could have a satellite that wouldn't have to be way up there, 22,000 miles in altitude at geosynchronous orbit, could put you in a much lower orbit, okay? But so the tether would be shorter, and this exponentiating length wouldn't be as bad. But in that case, the satellite is orbiting the Earth with some motion relative to the ground. And so to compensate for this, what he did was he spinned it, and the bottom of the tether was going in the reverse direction from the orbital motion, so that for a brief period relative to the ground, the bottom of the tether would have zero velocity. And you could hop up, in other words, you'd be there waiting for it, and it would come on down, and you could grab it at just the right time, and then you could climb the tether and get up there. Now, if you did this, you could get up to the center of the orbiting system, which would then place you in a stable orbit. But it had a number of problems. One is, you see, as the thing spins, this centrifugal force, which at the point when the tether is down, adds to gravity. And so that adds to the stress on the tether, in addition to that created by the Earth's gravity. And then you had the problem of momentary, you had to catch it at a particular moment, and so forth. And while this actually did advance the idea of the skyhook significantly, a couple of orders of magnitude in terms of its feasibility, it's still placed outside of the realm of existing materials because of the additive nature of the centrifugal force on the tether and the Earth's gravity. Now, what I'm advancing here, I don't know if it's original or not. I haven't seen it in the literature. So if it is, probably it just hasn't gotten enough play, in my opinion, because I think it's a workable idea. Is what I call a hypersonic skyhook. And what this is a tether whose satellite, which moors it, is in some orbit going around the Earth, and it's in an equatorial plane orbit. That's important. But it doesn't have to be in geosynchronous orbit. Now, the faster the satellite goes, the lower its altitude is. So those are the two variables you trade. And also as the faster it goes, the more the centrifugal force with respect to the Earth is. But in this case, the centrifugal force is all outward. It's anti-gravitational. And this actually helps you a great deal, because now you have the centrifugal force term on the tether not adding to the gravity term and leading to a more rapid exponentiation of the thing's size, but subtracting from it and greatly reducing the way the tether is blowing up on you. So it's getting shorter, and you have a weaker gravity field to deal with the more you come in. So let's see what happens. Let's go to the next, well, before we do that, let me just explain how this would have to work. This thing is orbiting the Earth, and that tether is not spinning. It is maintaining a radial orientation with respect to the center of the Earth. So it's orbiting with maybe a ground track velocity of, pick a number, 4 kilometers a second, for example, which is Mach 12, all right? And then you would have to have some trans-atmospheric aircraft that could basically hop out of the atmosphere. The bottom of the tether is sort of just above the tangible atmosphere, perhaps at an altitude of about 100 kilometers. And this thing would hop out of the atmosphere with a ballistic velocity of 4 kilometers a second, which is half that of orbital velocity in this example. And so it would approach the tether with zero relative, or near zero, as much as you would like it to be, a small relative horizontal velocity. But of course, it would be, as it were, falling. So what you would have to have on it would be a set of vertical rocket jets that for a certain period of time during the final approach would exert a thrust equal to the system's weight, so it would not fall. In other words, just like a rocket does that has to land. So to nullify its vertical falling velocity, and then it could achieve a soft rendezvous and dock with the bottom of the tether. Then it latches up, and at that point the payload could be lifted up the tether along a series, a cable car arrangement of some type. So let's see what happens here. Can I have the next slide? This is a graph showing the taper ratios for hypersonic tethers. Now, the bottom axis there, the velocity of the tether starts at 0, which would be one of Pearson's geostationary satellites. It would be a classic Skyhook. Okay? And what I have there is graphed is 3 different kinds of tether materials. These tether materials are rated with what they call a characteristic velocity, typically in kilometers a second. And I have there the white boxes would be the weakest tether with a characteristic velocity of 1.2 kilometers a second. You can go out and buy that stuff today. That's Kevlar. And then I have another bar, the middle one, which is a characteristic velocity of 1.6, which some people claim in the literature you can go out and buy today, although I'm not acquainted with where. And then the final, the lowest line there is a characteristic velocity of 2, which is probably achievable without getting too futuristic about things. Now, on the vertical axis there is the log to the base 10 of the taper ratio. So 10 on that axis is 10 to the 10th. Okay? So you can see, for instance, if you take the thing with a characteristic velocity of 1.2, that is the top line, the white boxes, if you used one of Pearson's stationary tether platforms, it would have a taper ratio of 10 to the 15th. Okay? It's totally unfeasible. Right? But as you increase the velocity of the tether, look at how that line comes down. It is dropping by, when you have a characteristic velocity of 4 kilometers a second, it now has a taper ratio of about 10 to the 3rd. It's come down 12 orders of magnitude. Now it's true it's not as elegant as the Pearson thing, where the cable is literally stationary with respect to the ground. Such, extraordinary machine appears in the Arthur Clarke novel, The Fountains of Paradise, and probably many other places. But that would require super strength materials. This doesn't. Taper ratio of 10 to the 3rd is probably a reasonable thing to undertake. As I said, that's off-the-shelf stuff. Can I have the next graph? Well, this is the same thing, except this shows the mass of the tether, assuming a 10-ton load at the bottom of it. What the mass of it would have to be. And once again, you would see, in the case of the lowest grade material there, the mass of the tether in a stationary Skyhook would be 10 to the 18th tons. Just an absurd number. I'm not sure how that compares to the mass of the Earth, but it may not be that big compared to the Earth, but it's big compared to things you want to launch. On the other hand, if you were to go at 4 kilometers a second there, you can see you're talking about masses of about 10 to the 3rd tons, which is still substantial, but not at all the same sort of thing. You're coming down to your 15 orders of magnitude in the requirement. Next slide. This table perhaps makes it a little clearer. Once again, we have the velocity of the tether in kilometers a second on the left-hand side, starting from 0 and going up to 7. And then you see the length of the tether, which drops from 36,000 kilometers to 200 at 7 kilometers a second. But 7 kilometers a second is not that interesting. If you can do 7 kilometers a second, you might as well go all the way to orbit without the tether. But if you look at intermediate results, say, once again, 4 kilometers a second, the length of the tether is dropping from 36,000 kilometers to 2,900 kilometers, I think is what it says, if I can read from here. And the mass of the tether is dropping, in this case, in the case of the intermediate strength of material, to about 800 tons, or the more advanced material, 200 tons. And a 200-ton object would probably be something that you could actually talk about launching into orbit for sure with a heavy lift vehicle. That's the kind of mass that Mike Griffin is talking about being able to launch for his lunar mission. So what we're talking about here is making the Skyhook achievable through taking a compromise in the purity of the concept. And once again, this is a 10-ton lift. If we were talking about simply using this to lift space probes that might weigh 100 kilograms, then these masses would come down by 2 orders of magnitude. And instead of 219-ton object, you'd be talking about a 2-ton object that you'd have to launch to orbit, which we could easily do today. So this is an approach to achievability for these kinds of systems. That's what it is. Now, by the way, the tether cannot stop at the satellite. It has to keep on going out in order for the satellite's center of mass to be at the design altitude that we're talking about. And if you keep moving out along this tether, what happens is you're gaining in altitude and you're also gaining in velocity, which means those locations, if you were to climb up there and let go of the tether, you would not stay in orbit at that altitude. You would fly out of there with some greater than circular velocity. And if you go up a little bit beyond the center point, you would simply fly into an elliptical orbit. But if you keep on going out along this tether, at a certain point, you will have translunar velocity. And if you go out a little farther, you'll have trans-Mars velocity. If you go out a little farther, you'll have trans-Jupiter velocity, and that's all you need. Because if you go to Jupiter, you can do gravity assist and then go anywhere in the solar system. So that this system would not only take you up to orbit, but could also take you up to locations at which, propellant-free, you could fire payloads all over the solar system. And as I say, you know, talking about 15 orders of magnitude reduction in mass compared to the more pure original Skyhook concept. And the reduction in the mass, well, you say, well, gee, but now you have to do 4 kilometers a second. And that's Mach 12. That's a lot easier to do than it is to achieve full orbital velocity because of the exponential nature of the rocket equation and the fact that we may have trans-atmospheric NASA-type vehicles. What if NASA, for example, turns out can't really make it all the way to orbit? Okay, maybe it can make it to Mach 12. It's a lot more achievable. If we believe what's an aviation leak, there are probably secret military aircraft today that can do Mach 6 through 8. So, there it is. Enough on the Skyhook. Now I want to talk about the magnetic sail. Next chart. Isn't it a color chart? Well, if we could just have the forward lights down somehow, it might help. Okay, well, the magnetic sail is a concept that I co-invented with Boeing's Damon Andrews about 4 years ago. And it has somewhat of an interesting history to it, especially I think would be interesting to this audience. A lot of you may know that around 1960, Robert Bussard came up with a concept for interstellar flight, which became known as the Bussard ramjet or the Bussard interstellar ramjet or whatever. And this concept involved a spacecraft which would have a scoop device, which presumably would be a magnetic scoop because of the required large size, that would fly through space, and as it went, it would use the scoop to collect interstellar material, which is to say protons, and then it would bring them into a fusion reactor where they would be burnt and produce energy, which would drive the thing forward. And the faster it went, the more rapidly it could collect propellant, and it required no propellant of its own except a little bit to get it started at the beginning. And the velocity would be essentially unlimited except by the speed of light itself. So you could approach asymptotically to the speed of light, which would give you unlimited time dilation, so you could fly to other galaxies or whatever within the lifetime of the crew. And when they came back, if any of the 10,000 banks that they had deposited $1 each in had survived, they'd be trillionaires. So this was just great. However, it had a number of problems with this concept. One is it relied on proton-proton fusion, which is an extremely slow thermonuclear reaction. It's once again, many orders of magnitude slower than deuterium-tritium fusion, which we're just barely trying to get work in the lab today. In fact, the sun, which works on proton-proton fusion, has a lower power density than a human body. That's how slow this reaction actually occurs. And there were other problems as well. Well, my collaborator in the mag sale, Dana Andrews, in the late 80s, was looking at this, and he finally got tired of trying to make the fusion reactor work, and he said, okay, all right, so this fusion thing isn't going to happen here, but we can still use the scoop concept, and what we'll do is we'll scoop up material, and then we will simply feed it into a conventional ion drive, which would be driven by an onboard nuclear fission reactor. And thus, while it would no longer have interstellar capability, it would still be a terrific system for interplanetary travel, and you would have totally gotten around the whole problem of making proton-proton fusion work. You would just use your rather conventional nuclear electric setup as far as the propulsion was concerned. So he started looking at this, and he ran into a problem, which was that the magnetic scoop he was using was generating more drag than the system was generating thrust. That is, in the course of collecting material, he was deflecting some material, and the drag that was being created was greater than the thrust. And that's when I got involved, because I have a certain background in plasma physics, and he asked me to look at this, and he said, look, is there anything you think can be done about it? And I looked at what he was doing, and at first I thought I could cure the problem, because he was using certain rather rough approximations in calculating the drag that was going on that were not really appropriate. And I thought maybe if we did a more exact calculation, we might find that the situation was not so bad. Well, when we did, we went to work together, we wrote a computer model, and we started calculating drags in a much more precise way. And what happened was the drag was about an order of magnitude worse. Okay. So the scoop propulsion concept was definitely deader than a doornail. And then I made a suggestion to Dana. I said, look, we got so much drag here, why don't we make some use of it? Let's get rid of the silly ion thrusters and just use this as a drag device and get our propulsion from the solar wind. And that's how the mag sail was born. And he agreed with that course of action, and we went to work analyzing it. And that's what we did. Now, what is the mag sail? Okay, now that I've said all that. The mag sail is a loop of superconducting wire that you deploy in space. And then you put an electric current in it. And the electric current will make the loop assume the shape of a circle. Okay, it will kind of inflate it through magnetic propulsion into a circular loop. And now it has a magnetic field. And here comes the solar wind, which is indicated in the diagrammatic portion of that picture by those arrows. Solar wind has got a velocity of about 500 kilometers a second, and it's made of totally charged particles. When they hit a magnetic field, it's like they're hitting a solid object. Well, and the question is, or they're hitting a substantial object, and they start pushing with the magnetic field. And they push it until they get to a point where the magnetic field becomes as intense in its pressure as the pressure of the plasma that's pushing on it. And that essentially defines a flow surface. And then the plasma proceeds to go around that flow surface, just like water going around a rock in the stream. But of course, there's also therefore drag imparted to the surface, which is transferred to the field, to the loop, and then the loop is connected by some shrouds to a spacecraft, and thus the solar wind is pushing the spacecraft. Okay. Now, solar wind only has a velocity of about 500 kilometers a second, which means that this device is unsuitable for acceleration of a payload for an interstellar mission, because 500 kilometers a second is not fast enough for a meaningful trip time to another solar system. But it can be used to decelerate a spacecraft that's being used on an interstellar mission, provided you have accelerated the spacecraft through some other means. And in the same way that one might decelerate a chemical rocket with an aero shield. And this has the effect of drastically reducing the amount of propellant and the whole requirements on the propulsion system that is being used to project the mission. I guess I'll proceed. Next slide. All right, as I said, at solar wind is 500 kilometers a second, and at 1 AU it has a density of about 5 million protons per cubic meter. And as your distance from the sun increases, the density of the solar wind goes down in inverse proportion to the square of the distance, as you'd expect, because it's flowing outward like that. Next slide. Now, if you're going to use this in interplanetary space, you're going to want to use high-temperature superconductors, because if you want to get a good thrust to weight on this system, you can't afford to have all the cryostabilization and refrigeration on the device that would be required to maintain at low temperatures a cable that was exerting the field. You want the cable to be able to exist in a superconducting state at the temperature of the ambient environment, perhaps with some insulation on it, reflective coatings, things like that, but not any serious cryostabilization. Now, in 1987, of course, there was discovered high-temperature superconductors by Chu and others, which actually have the required temperature that we would need to make a cable that we could run in space without cryostabilization, just with passive coatings and so forth. Now, these new high-temperature superconductors do not yet exist as practical cable, but I'm quite confident that before this decade is out, they certainly will. There's literally billions of dollars today that are going into solving exactly that problem in laboratories all over the world. And in the performance, you know, if you want to analyze the performance of a device like this, fundamental is the current to mass density of or current to area density or whatever of the superconducting wire. And what we're going to assume here is that the cables that will be developed will be able to have the same current density within themselves as exists today in low temperature superconductor niobium titanium, which is the most common low temperature superconductor, which would be 1 megaamp per square centimeter. Okay. Now, it's kind of interesting. I wrote a technical paper on this for a journal a couple of years ago, and one of the reviewers wrote in and he said, well, this is, you know, a cute idea, but it's absolutely impossible because for the following deep quantum mechanical reasons, it will never be the case that a high temperature superconductor could have a current density within 3 orders of magnitude of a low temperature superconductor. And then between the time when he wrote that comment and when I received it, somebody had demonstrated a high temperature superconductor with 62% of the current density of the low temperature device. So that was made it easier to answer to. It was real good that happened because I did not understand his quantum mechanics at all. Couldn't have about that. All right, next slide. And we're also assuming, by the way, the same mass density in these wires as currently exists in the high temperature superconducting material, which is about 5 times the density of water. Okay, there's a number of ways you can analyze the mag sail, basically 2, and we did both. One is you could look at the solar wind as a collection of individual proton particles, each with its own trajectory and its own fate. And then you set up the magnetic field and you write a computer program in which you fire these particles into the magnetic field and you track them one at a time in all their little directions they go off in, and you calculate the momentum change on each particle and you add it all up and you get a net thrust. It's sort of what they call a Monte Carlo technique. And we did that first. And we got a certain result. And then later on it was suggested to us by Joel Sercel, who's at JPL, who occasionally writes columns for Ad Astra, that we analyze the plasma instead as a fluid dynamic model, like water and fluid dynamic drag. And he said, that sounds like a good idea. And I went off and I derived a whole bunch of equations and so forth. It turns out that one you can actually do analytically, although the derivation is rather involved. And we came out with a certain number. And interestingly, the 2 numbers were fairly close to each other. They were were within about 30% agreement. So and you think the truth about a plasma is somewhere in between the fluid and the particle model, and so we kind of have it bracketed, and we're reasonably confident about the kind of performance you would get. Next slide. I'm not going to discuss the particle model because it's just it's a computational exercise with individual particles tracking them out. The fluid model, the way you do that, and the basis of the fluid model was established well before me by the people who do calculations of the Earth's geomagnetic field and its interaction with the plasma limb. And basically what you have is, in the third paragraph, you can see the relevant equation. You take the magnetic pressure, which is the magnetic field squared divided by 2 mu naught, where mu is this magnetic constant. And that equals the dynamic pressure of the plasma, Q, which is the density times its velocity squared over 2, times cosine squared theta, where theta is the angle between the free stream velocity of the solar wind and the normal to the magnetospheric surface that's being created by the loop. And you set those equal, and you can determine where the surface has to be through a somewhat involved procedure. And the magnetic field that you have to use is not the actual dipole field of the loop, but an increased field, because what's happening is the plasma is taking the magnetic field that's been spread all through the universe, and it's scrunching it up into this comet-shaped magnetosphere, and thus making it more intense than it would otherwise be. This actually adds to the effectiveness of the device. Well, anyway, you go through all this, and next slide. And I've pulled about 6 pages of equations here, hopefully. Oh, this just illustrates the concept, this in a geospherical context. Solar wind compressing the Earth's magnetic field, and you can see that little red arrow there. That's the angle theta between the free stream velocity and the perpendicular to the magnetospheric boundary. Next slide. And you end up deriving lots of equations. Next slide. And more equations. And the bottom line answer, you can't possibly read it or understand from where you're sitting, is there on equation number 10, and it tells the drag to mass of the mag sail as a function of the current to mass ratio, the loop's diameter, its current, and everything else, and the solar wind mass and velocity. By the way, I've got a technical write-up on this, which I think what I'm going to do is I'm going to put it on the NSS literature table and ask them to sell it for $1 each, all proceeds to the NSS, with the idea that if people want to read it, they'll pay rather than just have it give out. I only have about 20. Which goes through all these equations and explains how they're derived. But, next slide. If you plug in numbers, for a mag sail with a radius of 32 kilometers, a magnetic field at its center of 10 to the minus 2 Gauss. The Earth's magnetic field is half a Gauss, so this is a weak magnetic field, but big in extent. This object would weigh about 5 tons. The wire itself would have a radius of a couple of millimeters. Okay, so it's a wire about like normal plug wire, but 30 kilometers in radius. It would weigh about 5 tons, and it would have a self-acceleration of 0.17 meters per second squared. 0.017. Now, to give you an idea, that is about 3 times the self-acceleration of an object in solar orbit, in orbit around the sun at the Earth's distance. Okay? So in other words, if we detract from that sum, let's say we have to reinforce it to deal with stresses and so forth, so it's maybe 2.5 times the self-acceleration, and we were to put an object there, and attaches to the mag sail, turn the mag sail on, the mag sail would experience negative gravity from the sun. It would experience negative 1.5 times the solar gravity, in fact, and move away from it in a hyperbolic orbit, because the mag sail is exerting greater pressure against the sun than the sun's gravity is pulling it in. Now, if you turn the mag sail down, didn't run it at maximum current, or if you simply pile more mass on it, what you could do is degrade the performance to the point where the mag sail was exerting equal pressure against the sun as the sun's gravity, and the object would move through space in a straight line. Okay? Because you would effectively negate it. Because the mag sail's force also falls off as the square of the distance from the sun, because the solar wind falls off in exactly the same way. Or in any thing thereof. Or if you, well, we'll get more into this later. Next slide. If you put the mag sail at a certain inclination with respect to the wind, you can also exert a force which aerodynamicists would call lift, that is a force perpendicular to the wind. And this enhances your repertoire of maneuvers. What we found is that the lift-to-drag ratio was about 0.14, not very high, but it turns out that you don't really need the lift. We can do almost every relative maneuver we require simply through drag, drag being radial force directly away from the sun. Next slide. If you calculate the energy in the mag sail that I just described, the 30-kilometer loop with 50 kiloamps in it, it turns out that it is about 22 kilowatt hours. So that if you had a 10 kilowatt solar array, you could completely fill the mag sail with current and energize it, as it were, in a little more than 2 hours. It's not a terribly formidable task. And while it's in use, it does not need any power, so long as you keep the current constant, because the superconductor has no resistance. There's also a hoop stress in the loop, but it's not that great. It's about 11,000 psi. Ordinary steel can take more than 100,000 psi. In fact, high-strength aluminum is approaching that right now. So that even if the superconductor had no strength of its own, a small amount of reinforcement equal to about 10% of the mass of the loop could react to the hoop stress. Okay. And for purposes of the analysis, I'm going to assume that we're going to need some, and I'm degrading the self-acceleration of the mag sail in accordance and reducing it to 0.15 meters per second squared, 2.5 times solar acceleration. Next slide. All right. Let me just add something. Inside of the Earth's magnetosphere, there is no solar wind. It's masked out by the Earth's magnetic field, as you saw in the diagram earlier. So is it possible that the mag sail can actually maneuver within the magnetosphere? And it turns out that it can. And Bob Forward, in fact, suggested that I investigate this, because earlier we were simply assuming we just have to boost the mag sail to a sufficiently high altitude so it would be outside the magnetosphere and then it can start to sail. But it turns out that by simply using the mag sail as a magnetic attraction device with the Earth's own magnetic poles, you can boost it through a series of what are called perigee kicks into an increasingly elliptic orbit, where upon a large portion of its orbit gets outside of the magnetosphere, where it can catch the solar wind and sail away. And we derived all the equations required for that. Next slide. Well, there's the equation. It's in the paper. The important thing about it is that the force goes as r to the 4th power. That is, if you were to go twice as far away from the Earth's center, the force would fall off by a factor of 16. So the way you have to do this is by keeping the bottom of the orbit pretty much at low altitude and pumping up the top. And that's how you maneuver this thing out of the Earth's influence. Next slide. And keep going. Keep going. Okay, this illustrates a computer simulation of the mag sail being used in this way. And you can see the time in days, and it's taking about 34 days to complete this sequence of perigee kegs. And what you can see under the perigee starts at 290 kilometers, and eventually at the end is still only 500 kilometers, which means its radius from the center of the Earth has basically not changed. But the apogee is increased from 300 kilometers all the way up to 67,000 kilometers, which is 10 times the radius of the Earth, and is basically sort of outside of the magnetosphere. And then you can catch the wind and sail off. Next slide. And you could do the same stuff within the magnetospheres of a number of other planets. Basically, you've got it. If a planet has a substantial magnetosphere, you can operate near it by repelling or attracting off of its magnetic pole. If it doesn't, you can catch the solar wind. And what you see here is that the Jupiter, despite its stronger gravity, has so much greater magnetic field that the mag sail would be a more effective propulsion device within the Jupiter system than it is close to the Earth. Saturn, less than the Earth, but not impossibly less by a factor of 5. Uranus, less by a factor of 3. And Neptune, also less by a factor of 5. In the case of Mars, which basically doesn't have much of a magnetic field, you would just operate with the solar wind. Next slide. This is speculative, I won't spend a lot of time on it, but I'll just mention the following. If you assume, we've been assuming all this time, equal current to mass density of the existing low temperature superconductors on the high temperature. And that's the basis of all this analysis. But if all of a sudden we skip a beat and get wild and crazy and just assume that we can do 40 times that, which who knows? I mean, I can't say that's possible. But the, until 1987, people would have said high temperature superconductivity was impossible. Well, if you could get that, the mag sail could take off from the ground, provided you take off from Bathurst Island in the Canadian Arctic, which is where the Earth's north magnetic pole is. And there's what you might call engineering problems here, because in the repulsive condition against the Earth, the mag sail is dynamically unstable. It wants to flip around and become attractive. So, okay, I'm not really proposing that we try to do this straight away, but it's a thought. The idea that you could have a device that could literally take off from the ground without any propellant whatsoever and achieve orbit. And in this case, by the way, it's not only achieving orbit, it's achieving direct Earth escape to Mars with the required current density of about 40 times the existing stuff. Okay, let's move on. Next. And now we'll go back to assuming the same current density as existing low temperature superconductors. How can we maneuver the mag sail around the solar system? Ordinarily with rockets, you always thrust tangent to your orbit so as to change it to another orbit. The mag sail is thrusting radially against the sun. Well, it turns out that there's some rather elegant ways you can maneuver a mag sail payload all over the place. See, as I said, the mag sail can exert a self-acceleration against the sun 2.5 times greater than the sun's own acceleration. So let's say, and therefore it can exert any fraction thereof. Okay? And there's a parameter that I call alpha, which is basically, if alpha is 1, the mag sail is off and the sun is exerting its natural gravity against the spacecraft. If alpha is 1/2, it means you've turned the mag sail up to the point where it's negating half of the sun's gravity. And you effectively have, as far as the spacecraft is concerned, the sun has suddenly been reduced to half of its current mass. If alpha is 0, the sun's gravity has been entirely negated and the thing is moving through space in a rectilinear orbit. If alpha is negative, the sun is exerting negative gravity on the ship. Okay, and as I said, the mag sail itself can have a performance all the way into the negative alpha range. Well, let's say you have a payload that is co-orbiting the sun with the Earth, but outside of the Earth's effective gravitational field. Okay, so it's orbiting the sun at 180. And now you turn on the mag sail, and you turn it on just a bit so as to reduce alpha from 1 to 82%, 0.82. Okay? We've now reduced the sun to 82% of its current mass. What will happen then is the spacecraft will instantly change its orbit from a circular orbit at 1 AU into a Hohmann transfer ellipse that would go from the Earth at periapsis all the way up to Mars's orbit at aphelion. Okay, so you would simply swing into that orbit. Now, when you get to Mars's orbit, okay, you then change the current of the Maxwell again, so as to reduce alpha in this example to 0.65. So now you've reduced the sun to 65% of its existing mass. You're basically using the Maxwell as kind of an anti-gravity machine here. And what will happen then is the spacecraft will then go directly into an orbit because its velocity will be sufficient with respect to a sun of that mass to be in a circular orbit in Mars's track. However, it will not be moving at the same speed as Mars because it's going around a smaller sun. So you can get to Mars at the wrong time and wait till Mars shows up because it's going faster than you. So what you've done is you've massively opened up the ballistic launch window to Mars. Instead of having to launch once every 2 years, you could launch any time at all and get to Mars' orbit and dawdle until Mars shows up. And then when Mars makes its appearance, you let go of the payload, which would then aero capture either into orbit or go and land on the surface. And then the Maxwell would then turn its current down so as to reduce alpha or increase alpha to 82%. The Maxwell will then drop out of Mars's orbit back into the Hohmann transfer ellipse to Earth. And when it reaches Earth, you turn the current off and you circularize at 1 AU. Okay? Now, if the timing on this is wrong, instead of going straight back to Earth, you just go to some intermediate location, circularize there, dawdle until the Earth goes into the proper location for a return, and then you make the appropriate adjustments and go. So what this basically enables you to do, a number of years ago, a lot of people came up with these ideas of these cycling interplanetary, they call them castles. They're basically habitats, quite massive, that would be in orbit, say, between the Earth and Mars. And if you wanted to go to Mars, you wouldn't have to go out in a small spaceship. You just take a small spaceship to the cycler, hop on there, live in luxury on your cycler with tons and tons of radiation shielding and all this stuff that you wouldn't want to launch for each and every individual mission, but it's in permanent orbit. You get on a cycler, and then when you get to Mars, you get off and you go to Mars, and you catch another cycle on your way back. This was a kind of an interesting concept, but a major problem with it was that the cyclers, it was very difficult to figure out cycling orbits that would intersect the Earth and Mars repeatedly and allow you to get a lot of utility out of these cyclers. Because you certainly wouldn't want to build this enormous cycler and only get to use it, once every 20 years. Okay? So the idea here is that by playing games with the sun's gravity and adjusting the orbits in this way, you can basically cheat against the laws of orbital mechanics and arrange things so that the cyclers can pretty much hit more or less every time. And also, since it requires no propellant, it's appropriate for moving around large masses. Next slide. Keep going. Well, keep going. This just shows how I calculated the alpha should be 82% to go to Mars. Keep going. Go until you come up to the table. It's kind of a table showing it's going to different places in the solar system. Right. Okay. This is Maxwell orbits without using lift to various destinations in the solar system. Now I have this parameter I call W. W is the weight ratio. It's the weight of the Maxwell plus payload divided by the weight of the Maxwell alone. Okay, so the bigger W is, the more mass you're taking in proportion to the Maxwell's mass. You want W to be big. And then if we use the performance of the Maxwell that we just discussed, and you you have to do two maneuvers to get to this planet. You have to go into the ellipse that takes you there, and then presumably you have to circularize once you get there, especially if you want to be able to use this trick of waiting for the planet to show up at your convenience. Well, so you have to achieve a certain alpha for the transit and a certain alpha for the circularization. And basically, the more mass you put on the mag sail, the higher W is, the lower performance you're going to get out of it, and the less you're going to be able to do in the way of changing alpha. So there's a certain W you can have to achieve the transfer orbit, and a certain W you can have to achieve the circularization. And those are listed in the two right-hand columns there. And the actual W that you can have to achieve the mission is the lower of those two numbers. And what you can see is that to go to Mars, you could have a W of 9.6, which means that the payload would weigh 8.6 units and the mag sail would weigh 1. Almost all of it would be payload. To go to Pluto, you could have a W of 5.1, which still means the payload weighs 4.1 units to the mag sail's 1. Still 80% of the mass is the payload. And to escape the solar system, 5. So that's pretty good. You can go all over the solar system without using any propellant. And by the way, you can do all sorts of tricks on this. You don't have to, these are slow, well, these orbits are like Hohmann's transfer orbits. They're a little bit slower because you reduce the mass of the sun that you're going around. But you can also go into fast orbits. For example, if you take one of these slow orbits and go to Mars, but then instead of turning the mag sail current down a little bit, you just turn it off, what will happen is you will drop into an orbit with an apoapsis at Mars and a periapsis near Venus, and which will do fast transits between Earth and Mars. So you can move the mag sail around in all sorts of bizarre orbits just by turning it on and off and up and down at the right times, without using any propellant whatsoever. Next slide. And I give the formula for calculating the transit time. Next slide. It's a little bit slower than an ordinary ballistic transfer, but not much. You can also do like the tau unit. In other words, if you go with a real low W, like W equals 1.25, you're going to have a negative alpha, and you're going to go screaming out of the solar system. And in this case, you get a final velocity of about 95 kilometers a second, and you'd reach 1,000 AU in 50 years. You could do better if you lower W. Next slide. And also the mag sail creates some shielding against solar flares by virtue of the fact that it has its own magnetosphere, just like the Earth's magnetic field does. Next slide. Okay, the final thing here. Okay, the mag sail as an interstellar brake. If you can accelerate a spacecraft up to a relevant interstellar velocity by some means, perhaps by using a fusion rocket, which if used a deuterium helium-3 fusion rocket, it could have an exhaust velocity theoretically as high as 5% the speed of light, which means you can probably achieve velocities if you're going one way of up to 10% the speed of light, if you don't have to do anything to brake. Or, for instance, Bob Forward has discussed many times the potential of the laser-pushed light sails, in which you'd have a very high-powered laser located within the solar system that would push on a solar sail, a light foil sail, and push it out of the solar system at very high velocities. That could also get you up to relevant velocity for interstellar flight. The question is, how do you stop at the other end? Well, you could use rocket propulsion in either case, but then you have to take with you all the mass required to decelerate the spacecraft through this gigantic delta V that you've put it on in the first place. And this would enormously inflate the mass of the mission or force you to go slow. Or if you use the light sail, Bob has this idea where perhaps you could detach the foil and reflect back at another foil and stop it, but then you'd have to be able to aim and focus the laser over interstellar distances, which could be rather hard to do. That could create a real problem, especially if the laser missed points and things like that. I'm not saying it's impossible, but it could be pretty tough. What this would allow you to do is use either of these concepts, the laser light sail or the fusion rocket, for acceleration, and then when you get near the planetary system that you're targeting, you deploy the mag sail, turn it on, and you will exert drag against the interstellar medium. In this case, the medium is basically not moving. You're moving, but that creates a relative wind with respect to the medium and creates drag. Next slide. This goes through the derivation. Next slide. Okay, this is, can you move it over a little bit so people can see it a little bit? The other way. Move it the other way. Yeah. This shows a bottom line equation here. And in this case, I'm assuming the ship got up to 10% the speed of light, and now we want to decelerate it. And what you see on the numerator of the equation is the velocity, 3 times 10 to the 7th meters a second, which is 10% the speed of light. And then it's divided by a factor, which is 1 plus 0.05 factor cubed. 0.05 times the time in years, factor cubed. So when t is 18, because it's 0.054, that 0.054 t equals 1, and 1 plus 1 is 2, cubed is 8, means that after 18 years, you have reduced the velocity from its basic velocity of 10% the speed of light to 1/8 of that. You've killed the large majority of the velocity. And you could go to a longer time using the mag sail and basically reduce it to insignificance. But within a fairly short amount of time, a couple of decades, you can basically eliminate this massive interstellar velocity and let some interplanetary class propulsion system take over and bring you to your planetary destination. And this, as I said, in the case of eliminating rocketry in favor of this, well, it basically has the effect of for instance, if you wanted to achieve 10% the speed of light and your exhaust velocity was 5% the speed of light, to accelerate and decelerate the ship to and from that velocity would require a total mass ratio of like over 50, because it's e to the 4th power. But if you just had to accelerate it to that velocity, it would only require e to the 2nd power, which is like 7. So if the ship had a dry mass of 1,000 tons, in one case the total initial mass would be 7,000 tons, and the other would be 50,000 tons. And that's what you'd save with the mag sail. And you'd also save a lot of time because the less massive ship could accelerate up to its speed faster. Next slide. So, I thought I'd save this for last. This painting was done for Ad Astra by Maxwell. And it depicts the mag sails in the flight. But basically speaking, what I'm saying here is that assuming we can get practical high-temperature superconducting cable, the mag sails can be made that can fly from low Earth orbit into any location in the solar system without using a drop of propellant. And they can also contribute a long way towards enabling flight to the stars by drastically cutting down the requirements of the propulsion system. Thanks. Do I have time for a question or two? Yes?
Just a piece of information in case you haven't run across it. Evidently, a Japanese group has been making 100-meter lengths of superconducting wire with carrying capacity within 1 or 2 orders of magnitude of what you're looking for.
Mm-hmm. That's interesting, and I'm sure it'll keep moving forward. Other question over there?
Have you looked at all the principles of using the superconducting wire to create the magnetic field strictly for shielding in terms of stations or other type of vehicles, strictly for the shielding value?
Well, it gives you a terrific shield against solar flares. You basically completely protect the crew against solar flares with this device. It does not do much shielding against galactic cosmic rays. They can sort of just, at least with the kind of magnetic fields we're talking about here, they fly right through it. Any other questions? Bennett.
Have you thought about what kind of power source you're going to use to feed your your coil?
Well, if you're in near Earth or Earth-Mars kind of interplanetary space, you could use solar power. The power requirements are not that large. We're talking about things in the neighborhood of 10 kilowatts of power. Because all you need is power to inflate it initially, and then inflate it again if you later on bring the currents down and up and things like that. If you're going into our solar system or interstellar space, you need a nuclear power source. But once again, there it doesn't have to be a very large one. All right, I guess I'll get off for the next speaker.